Okay, great. Hi, everyone. Let's get started with our final remote lecture. So in today's lecture, we are going to be introducing neural networks. This is a fairly complex topic, and we're going to spend a decent amount of time in this course on neural networks. And so in today's lecture, we'll just get an introduction into this new class of models, and afterwards, we'll be working with these models for quite some time. Okay, so a couple of announcements before we get started. The second homework is, of course, due tonight at midnight. So no late homeworks are accepted again in the course, but we will be dropping your lowest homework score. So if you can't complete this one for whatever reason, no worries. We'll go ahead and drop your lowest score. So the second reminder here is that the in-person lectures for this course are going to resume on Monday. So from this point onwards, there will be no more remote lectures. So I hope to see you all in the lecture hall on Monday. Coming up on Friday is the midterm exam for our course. So as promised, there is a sample midterm exam sort of in progress. I'm currently working on that. So I hope to get that sample exam out to you guys as soon as possible. Most likely it's going to be coming out on Monday evening. I know it's a little bit later than would be ideal, but that's just when I'll be able to get it to you guys. And I'll also point out that this week our discussion sections on Thursdays are going to be a midterm review session. So for the first part of that discussion section, we're going to be reviewing that sample midterm exam. And then for the rest of the discussion section, there will just be a sort of open Q&A midterm review. So as you're reviewing the slides and reviewing the recorded lectures, make sure you come prepared with questions for those discussion sections. And hopefully it'll be a pretty useful resource for studying for the exam. Okay, so in today's lecture, we're actually going to first do a very brief review of logistic models. We're going to see a few ways you can extend logistic models. So primarily so far, we've only seen how to use logistic models for binary classification problems, and we'll see how to use these models for multi-class problems. And then for the majority of today's lecture, we're going to be introducing neural networks. So I've shown you guys these review slides already, but it can't hurt to have it fresh in your minds, like what a logistic model is. So for binary classification problems, for a logistic model, what we'd like to do is model these conditional probabilities. So what is the likelihood of the label being y equals 1 given a data point x? And we're going to achieve this using our logistic classifier model. Okay, recall that to actually compute these logistic models, we first compute this score function z, and this score function is just a linear function, essentially a linear combination of the weights in the model times the features. And then to get the actual output class probability, the output of the model f of x, we take the sigmoid function and apply that to our scores. And again, we apply the sigmoid function in order to transform those unnormalized scores, those just arbitrary numbers, into valid probabilities. To learn a logistic model, what we minimize is the binary cross-entropy loss function. And if we minimize this loss function, we're maximizing the model's predicted probability for the correct classes in our training data. We can, of course, use our handy tool here, the gradient descent algorithm, to actually minimize this loss function. And here at the bottom of the slide, I've got an expression for the gradient of the binary cross-entropy loss. So in last lecture, we saw that there's a pretty ugly involved calculation required to get this gradient expression, but the gradient expression itself is something pretty straightforward to compute. So this is logistic models in a nutshell. So now that we've seen more or less all of the basic details of working with logistic models for binary data, let's see a couple of extensions of these models. So one of the main limitations of logistic models as discussed so far is that we really only know how to make them work for binary classification problems. So let's say instead that we have C classes. So capital C is the number of classes in my problem, and I have more than 2 of them now. The basic idea behind defining a multi-class logistic regression problem is that I can define one score function per class each score function now having its own parameters. So what I really mean by that is that I now have a score function for the kth class, z sub k, where I'm going to allow k to vary between 1 and c. So I've got one score function for each of our c classes. This score function takes in a data point, and it has some parameters associated with it. Here I'll call it theta k. So theta k is my collection of parameters for the kth score function. And I'll denote these parameters by theta k0, theta k1, so on and so forth. So this is the usual notation for the score function in a logistic model, except now I have this additional subscript k because I'm working with the kth class. And to get the actual output of this kth score function, I just do the usual linear model. So I've got just a linear combination of the parameters for my kth class times my data point. So nothing new here other than we're introducing one score function per class. Good to keep in mind that by theta sub kj, I really mean the jth parameter for the kth class in my problem. So if you just count up the total number of parameters we have now, it's a total of c times d plus 1 parameters. So in the standard binary logistic model, we've got d plus 1 parameters. We've got now c classes total. So of course we have c times d plus 1 parameters. And I'll probably use just capital theta here. I guess this is actually a lowercase theta, disregard that. But we'll use theta here to denote a vector essentially corresponding to all the parameters in the model. So it's just a concatenation of all my theta sub k's. Okay, so here I just rewrote my score function expression from the previous slide. So in a standard binary logistic model, we of course need some way of turning these scores into probabilities. And to do that for more than two classes, we're going to use something called the softmax function. And really, this is a generalization of that logistic or sigmoid function to the setting where we now have greater than two classes. So the way we're going to get the predicted probability for the kth class, so what probability is my model assigning to the kth label in my possible set of labels for a data point x given parameters theta? I'll also write f sub k for this number, i.e. the model's output for the kth class. And I have an approximate sign here because the model's output, f sub k of x, is not exactly the true probability of the label being k given data. It's just an approximation to that. If it was perfect, then we would have the perfect model and we would be very happy machine learners. But of course, we really only have an approximation to these sort of true probabilities. And the way we get these model outputs is we're going to apply this so-called softmax function to our unnormalized scores. So to get the kth output of my model, where k can vary between 1 and capital C, what we're going to do is we're going to take, in the numerator here, e to the z sub k. So I take my kth score and I exponentiate it. And then on the denominator here, I sum up the exponentiated values of all of the other scores. So on the bottom, I exponentiate all of my scores for all of my classes and then sum them up. So this expression here is probably a little strange if it's the first time you're seeing it. You might not be sure where this is coming from or what it's doing, but I think it's actually a fairly intuitive thing where this comes from. So really this softmax function, what it's doing is it's taking our C unnormalized scores, these Z sub k values, then it's going to exponentiate all of them so that they're positive values. So e to the any number is going to be some positive number. And that's really what's happening in the sort of numerator. It's making the kth score now a positive value. And the reason we need to do that is because our scores coming from our linear model could be negative numbers. We don't sort of a priori have any control over these scores. But of course, if we want them to represent probabilities, we're going to need them to be positive numbers. The next thing we're going to need in order for these outputs of our model to be valid probabilities is that they need to be smaller than 1. So the first bullet point, again, takes care of the fact that they're positive, and the second bullet here is going to normalize them so that they sum to 1. So all in all, our softmax function has the effect of turning our unnormalized scores into a valid sort of probability vector. So it plays a very similar role to the logistic or the sigmoid function in the sense that it's ensuring that our model is actually outputting valid probabilities. Okay, so this is exactly what I had on the previous slide, so I'm not going to spend too much time going over it here. But let's look at a quick example, a simple numerical example, just to give you some more of a concrete idea of how this works. So let's say I have 4 classes in my problem now. And if I have some weights in my model, I can get scores where I have 1 score for each class. And again, these scores are coming from just essentially a linear combination of data with parameters. So I've got 1 score per class, and maybe I have these numbers for my 4 scores. My first step in computing the softmax is to exponentiate every single one of these scores. So 8.17 is like e to the 2.1, 0.25 is e to the minus 1.4, so on and so forth. What you should notice is that when I exponentiate, I turn all my scores into positive numbers. So this negative number becomes a positive number. Then to get the softmax, I'm going to take each of these numbers here and divide it by the sum total of all of the numbers. So I'll take 8 and I'll divide it by 8 plus 0.25 plus 3.3 plus 1.35. They'll get 0.62 and so on and so forth. And this has the effect of turning these unnormalized scores, again, just arbitrary numbers, into now a vector of probabilities. And if you actually sum up all of these numbers, you'll see that it sums to 1. That's exactly what we need for it to represent sort of a distribution over the possible labels. Now, we have to pick exactly 1 label out of these 4 possible labels. And so essentially, what our model is saying now is that, okay, I think there's a 62% chance that the label is 1. There's a 2% chance the label is 2. There's a 25% chance the label is 3. There's a 10% chance the label is 4. So we'll see in a little bit that you can actually also use this softmax function in neural networks. We won't see that in today's lecture, but when we get to multi-class neural networks, we'll again be using this softmax function. And as I pointed out, if we sum up all of the model outputs, if we sum up all of these probabilities, we'll get a value of 1 for every distinct input x. Okay, great. So we've set up or defined our logistic model for multiple classes, but the remaining question, of course, is how do we actually train such a model? Well, you might have guessed we're going to just go ahead and use gradient descent. It's one of the most popular algorithms in machine learning. For our loss function, we're going to be using what's called the cross-entropy loss. And really, we saw a special case of this already with the binary cross-entropy loss when we had binary classification problems. And sort of the general formula for this cross-entropy loss is L sub CE is a loss function taking in parameters theta. And to obtain this, I'm going to sum over all of my n data points in my training data. And I'm going to do negative log of f sub yi of x sub I. So lots of symbols and subscripts here. But really what this means is that I'm going to take the negative logarithm of the probability predicted by my model for the correct class, y sub I, on my ith training data point, x sub I. So again, if I have 3 classes and the correct class is 2, the value I'm going to stick in here is the predicted probability from my model for the second class. And intuitively, what this loss function is trying to do, if we minimize it, is maximize the model's predicted probability output for the correct classes in my training data. So very similar to the binary cross-entropy loss, we've just now got multiple classes. Another drawback of logistic models as we've written them is that they all have linear decision boundaries. So all the logistic models we've seen so far, if you actually work out an equation for their decision boundaries, which we did in a previous lecture, which highly encourage you guys review that one. you'll see that it has a linear decision boundary. This is obviously not very desirable because we could have problems where a nonlinear decision boundary would be a lot more appropriate. So sort of the expressive power of these models is fairly limited. Is there any way that we could somehow adapt our logistic models to get a nonlinear or sort of curvy decision boundary? And so if you're watching along with this lecture, I would normally maybe pause and ask the audience to think of a few ideas of how they might introduce nonlinear decision boundaries here. But I encourage you guys watching at home, wherever you might be watching. It's Friday night, maybe you're out watching this at a party or something. To really think about how you could change the logistic model to get a nonlinear decision boundary. Okay, so pause here. I'm going to move on. Spoiler alert coming up. So one way to do this is to actually do something very similar to like what we had seen for turning a linear regression model into a polynomial regression model. The idea is we can compute these sort of feature expansions of our data. So we could essentially take a polynomial feature expansion, say, and then apply sort of the standard logistic model on top of those new features. So we could, square our features, take the product, and so on and so forth. Exact same idea as polynomial feature expansions, except now we're doing it in the context of a logistic regression model instead of a linear regression model. Okay, this is quite useful. We can train our logistic regression model in exactly the same way we had done previously. Really, in effect, all we're doing is kind of creating new features from our data, and then we can just, train logistic regression exactly as we had done previously. And in effect, what we get out of doing this is nonlinear decision boundaries in our original data space. So if, for example, you compute a degree 2 polynomial feature expansion of your data, like the example in this line here, then you'll get quadratic decision boundaries. So the decision boundaries themselves actually are going to be governed by quadratic equations. There's a couple of problems with this approach, though. The main big problem here is like, how do you choose which features to add? How do you pick the polynomial degree? How do you know polynomials are even a good idea? Maybe you want to use trig functions. Maybe you want to use something else entirely. So, for many years in machine learning, a lot of work, went into designing these sort of feature expansions in a task called feature engineering. Some machine learning engineers still do this nowadays, but it's been supplanted a little bit by more modern methods. But it's a very difficult question. How do we know what features to choose? Another drawback is that if you add more features to your problem, doing these polynomial feature expansions, for example, it's going to lead to slower training and predictions. So our logistic models scale in terms of the number of features in both training and prediction time, as well as requiring more memory usage. So we can get nonlinear decision boundaries, but at the cost of a couple of caveats here. Okay, so that is the final part of our discussion on logistic models. So let's summarize in sort of a very high-level overview of what we've seen. So logistic models, again, have two parts: a linear weighted sum, the score function, and then we have a sigmoid function applied on top of that that takes that weighted sum and turns it into a probability. It's fairly straightforward to generalize from two classes to, should be capital C classes here, sorry, small typo, by just having a set of weights for each class, so one score function per class. And you can learn logistic models using this log loss function, or I call it the cross entropy loss function, and using gradient descent as we kind of typically do. The strengths of logistic models are that they're pretty easy to fit. Simple expression for the gradient. Loss function is actually convex. We didn't discuss this very much, but it is indeed a convex optimization problem. And another strength is that they're very easy to interpret. So we saw at the end of the previous lecture how you can sort of crack open your logistic model, inspect the individual weights, and those individual weights tell you something about how the features influence the predictions in your data. We'll see in a little bit that neural networks, very difficult to interpret. And in fact, there's a whole field of machine learning just focused on trying to, build methods for interpreting the outputs of neural networks. So a very difficult problem for more complicated models, and it's sort of an open research question. One of the main weaknesses of logistic models is that you really only have linear decision boundaries, and this just might not be sufficient for harder classification problems. Okay, so now that we've finished our discussion on logistic models, let's go ahead and get started with neural networks. So first, a bit of history about these models. So really, the way I view it is that there's three phases in the development of neural networks. In the first phase, from about the 1950s to the 1970s, people were using very, very simple models that looked a lot like logistic regression. And these didn't have any hidden units, which we'll see what that means in a little bit. And after about 20 years of work on these, the initial enthusiasm on these models eventually died out because it just wasn't working. In the second phase, from about the 80s to the 2000s, there was an invention of this algorithm called backpropagation. And what this backprop algorithm lets you do is train models that are bigger and bigger and bigger. But of course, if we have a very large model, it's going to take a long time to train. And it's also going to require quite a bit of data. And so, back in the 80s, computers weren't so great as we have today, and data was a lot scarcer. And so these sort of external limitations on these models really caused enthusiasm to once again die out. But nowadays, in the sort of third phase of neural networks, starting from about the early 2010s, people really have at last been able to demonstrate for the power of deep learning models. We'll see exactly what that means in not today's lecture, but perhaps in a few lectures. One technique here that sort of powered some of these breakthroughs is called stochastic gradient descent. So we'll see this algorithm in a little while, not in today's lecture, but it's a variant on gradient descent that actually lets you train very, very large neural networks on tons and tons and tons of data. And lately there's been a whole host of commercial successes of these models. Everything from ChatGPT and DALL-E and Stable Diffusion. All of these models are deep neural networks. And of course, there's a whole lot of enthusiasm about these models nowadays. In fact, it's almost difficult to not work on neural networks if you're in machine learning. They've kind of sucked all the air out of the room, if you will. Okay, so one thing that I'd like to introduce to you guys, I showed this in the very first lecture of the course, but that was a few weeks ago, is this ImageNet dataset. So this is a huge dataset. It has more than 10 million images in it, and it corresponds to a very difficult classification problem. So there's over 1,000 different class labels in this dataset, ranging from things like pizza and maybe taxis to dogs and specific dog breeds. So it's a very general image classification data set. And sort of the point of this data set is that it's supposed to be a test bed for evaluating or benchmarking general image classification algorithms. And I bring this data set up because it really sort of drove a lot of the developments of neural networks, at least in recent years. So, for example, the error rate, sort of the misclassification rate on this data set for many years was pretty stagnant. And despite the efforts of, say, the computer vision community and many other people in computer science, there really wasn't much progress on this task. So between 2010 and 2011, there was only a very small increase in performance here. But in 2012, deep learning came along and really sort of cracked this problem wide open. So we see in just 1 year, there was a massive increase in performance in these models, thanks to the advent of something called AlexNet. So if you've heard of what like a convolutional neural network is, AlexNet was really one of the first large scale, extremely successful applications of convnets. And of course, since then, deep learning has kind of been an unstoppable force within machine learning. Okay, it's not just image classification where deep learning has really taken off and sort of empowered major breakthroughs. Another really good example is sort of this game playing domain. So on the x-axis here, I have time, essentially 1995 to 2020. And on the y-axis, I have the rating of the best Go playing agent. So Go is this really difficult board game if you're not familiar with it. And just like for image classification, sort of progress on this problem was, pretty slow. This is a pretty flat line here. There's not a whole lot of breakthroughs in this problem. But then right in about sort of 2010, and especially in 2015, we see there's sort of discontinuities in these curves. And really, these discontinuities are thanks to machine learning techniques being introduced to this problem. In particular, deep learning really powered this kind of final breakthrough here into superhuman level Go playing agents. Okay, so why are they called neural networks? Where does this come from? Well, there's this really old model of the neuron, which is the basic cell in your brain that people in machine learning kind of took inspiration from in order to develop these models. So these neurons are sort of a very basic model introduced by neuroscientists, I think in the early 70s for these models, treats neurons as a sort of computational unit where they take some input from their neighboring neurons and produce some kind of output that they then send to their sort of downstream neurons. So they're kind of cells that like communicate with one another. If there's any neuroscientists watching this, don't quote me on the details here. But these individual sort of computational cells that communicate. Nowadays, most modern machine learning techniques are not so biologically inspired as sort of the original neural networks. We've really stepped away from this inspiration, but at least the name has stuck around, sort of more of a historical artifact than anything else. Okay, so just a reminder on this sort of block diagram for how we might draw a logistic classifier. The idea being we have our inputs, our features. We kind of feed them forward through this computational diagram where we take a weighted sum of those features and then pass it through the logistic function. So it's a graphical way of representing a logistic model for two classes. So let me draw this in a slightly different way. So I've got my input data, x1 through x3, and this bias unit here. I take a weighted linear combination of them, and I apply my sigmoid function, and I get some output here represented by this dot. So this dot on the right-hand side represents the output of a logistic model. I'll call this output h of x for reasons that'll be clear in a few minutes, but h of x, as I've written it on the right-hand side equation here, is nothing more than my binary logistic model. So nothing new. What I'm going to do now is something a little interesting. What if I have a second logistic model? What I mean by that is that I have some weights for my first logistic model in red, and I have some different weights for a different logistic model in blue. So in this kind of pictorial diagram, I now have sort of two computations being done on my original data. I've got this red dot, which is some function of my data. It takes the data as an input and produces some output. I've got a different function here in blue. These functions are both just logistic models. They're some kind of computation of my data. Okay, so one way to think about what we've just done is that we've taken our data and we've sort of created some new feature representation of this data. So I take my data and I transform it in some kind of way. And you can really think of this as creating new features from my data. So almost like how in polynomial feature expansions, we take the data and create new features, new representations of this data. That's exactly what I've done here. I've got sort of two new features, this red dot and this blue dot. But in contrast with a polynomial feature expansion, this red output and this blue output are now learned. They're not some fixed function that I had to, pay a machine learning engineer to go implement and come up with. They're learned from data. There are weights associated with these computations that I can use to update my model. So in some sense, I've created sort of learned feature representations of my data. Okay, so now that I have some new features, some new data, If I would like to do classification, well, our favorite classification algorithm right now is logistic regression. So I can take my new features, my red dot and my blue dot, and just stick them into a logistic model. So again, to summarize, I take my data, I compute new features based on this data using some learned logistic models. It's my red dot and my blue dot. I have new features that I can then put into a third logistic model, and that's going to be represented by this black output here. So at the end of the day, what I've done is I've designed some kind of some sort of feed forward computation going from my data to new feature representations to my model output. And this model output here is exactly just the usual class probability in a binary logistic model. So we now have our first neural network. So congratulations, you made it. We're going to see much more complicated examples of these neural networks. This is really, pretty much the simplest case we could have, but this is indeed a neural network. And so you can see how neural networks really build on this concept of logistic models by just kind of stacking them together in order to learn better and better feature representations. So this basic idea of transform the data in some learned way with some weights that can depend on the data and then fit a model on top of that is going to take us very far. So really the reason that we do this in the first place is that logistic models, as we pointed out, have linear decision boundaries. We don't know what features we might want to create from the data in order to create nonlinear decision boundaries. So by allowing our sort of feature maps, these red computations and these blue computations, to be learned from the data, we have an automatic way of learning nonlinear decision boundaries. So, very powerful idea. Let's introduce a little bit of terminology that we're going to be using for the rest of our sort of neural network discourse. So when I say hidden units, what I mean are the nonlinear functions of the inputs sort of in the middle of my network. So they're called hidden units because they're sort of not visible. They're sandwiched in between my input here, my data, and my output here, my predicted probability. So they're sort of hidden. They're internal to the computation. They're nonlinear functions of the inputs because they're logistic models. So again, we get this output h1 of x by taking a weighted linear combination of my data, sort of represented by these lines here. And then I apply the sigmoid function, or the logistic function, on top of that linear combination. So h1 of x is indeed a nonlinear function of my data. And this nonlinearity is quite important. Here we use the sigmoid function as our sort of nonlinearity. It's a way of turning a linear function into a nonlinear function. It's composition. But in practice, other functions are also used rather than the sigmoid function. So what I mean by that is we can take a weighted linear combination of my data and then apply a different nonlinear function on top of that to get a nonlinear output. And these nonlinear functions are almost always called activation functions. So if you've heard of activation functions, they're the nonlinearities in your network. We oftentimes think of networks in kind of terms of layers or sort of stages of computation. So in my first layer, my input layer, this is really just my data. So I've drawn sort of one dot here for each of my different components of my feature vector. Then I have a hidden layer, which is both of these dots kind of combined. It's the first stage in my computation. So this is the hidden layer in my network. And then I have this final dot here, which is my output layer. So this is a neural network with a single hidden layer. We'll see later on you can create networks with multiple hidden layers to have even more complex models. Yeah. We oftentimes also refer to layers of weights. So in this previous slide, I'm referring to sort of layers of nodes in my network or sort of layers of values. But we can also think about layers of weights. So again, associated to each one of these hidden units is a collection of weights. essentially the weights in the corresponding score functions of those logistic models. And so we can talk about sort of a layer of weights, which are all of the weights in this corresponding layer, essentially corresponding to the computation for this first hidden unit and the second hidden unit. We, of course, also have a second layer of weights corresponding to the computation required from taking us from the hidden units to the output of our model. So this is our sort of third logistic regression model. It's the weights for this corresponding computation. Oftentimes, we'll write the weights associated with each sort of computation with the associated sort of line connecting the hidden outputs to the next node in the diagram. So for example, f of x given theta is the sigmoid function applied to beta 1 times h1 plus beta 2 times h2 plus beta naught times 1. And we'll put some more symbols and some more math to this in a second, but just good to know that's what these b's or these betas here are representing. Okay, so in the previous diagram, we saw a neural network with three-dimensional input, a two-dimensional hidden layer, so it has just two h values, and a one-dimensional output. But in general, you can have a d-dimensional input feature vector, so your inputs can really have any dimension that you want. We have some associated first layer of weights, so we have one weight sort of per edge in our network. In general, we can have a total of capital M hidden units, where the number of hidden units in a network is actually a hyperparameter of the model. It's something we're free to choose. And then we have a second layer of weights associated with kind of the computation of the output of the model. And at the very end of the day, we have our output, which is most often a predicted probability, although it doesn't need to be. You should notice here we have these kind of ones here with those associated nodes. These are often called bias terms. And really all these are doing is kind of accounting for the fact that in a general linear combination, we have those like theta naught terms that they're not multiplied with the data, they're just added to the data. So these are often called like bias units or bias terms. For the total sort of collection of parameters in a network, we'll just use theta to represent that. And that's the collection of all the weights in all of my layers. So it's all the weights in the first layer, it's all of the weights in the second layer, all kind of lumped together. In total, if you have a neural network with a single hidden layer and m hidden units, as drawn on the slide, well, there's going to be d plus 1 times m plus m plus 1 total parameters. So this is on the order of d times m parameters in the network. And again, this is just by essentially counting. So I highly encourage you guys to maybe pause here, work out on pen and paper why exactly it's this number of parameters. It's a really good way to check that you understand what these models are doing. Oftentimes, these networks are called feed-forward networks or multi-layer perceptrons. So they're called feed-forward networks because sort of the information flows from the left-hand side to the right-hand side. So there's sort of a left to right computation going on. There's something feeding forward. They're called multi-layer perceptrons because they have multiple layers and they're connected to this older algorithm called the perceptron algorithm that we didn't take the time to go through in this class. So what kinds of functions can you represent with a neural network? What kinds of decision boundaries can we get? If we have a really simple logistic model, say represented by this network, where there's two inputs, x and y, the weight associated with x is 100 and the weight associated with y is 0, well, we get a simple sort of logistic model that looks like this. So sort of the flat plane here represents the input data, and the vertical plane here represents the output of this very simple neural network. So we see it sort of has two regions, right? It has this lower region and it has this upper region. And again, this is the function now representing the output of this network. If we have a network that is now sort of a combination of two logistic functions, i.e. it has now two hidden units, well, we get actually a significantly more complicated output from our model. It not only has two regions, but it has this region has another flat region up here, and it's got a third region down on the other side. So we can get pretty complicated functions by introducing some hidden layers into our network. And if we introduce even more hidden layers, for example, this network on the left-hand side, won't go into the details, we can get a pretty complicated shape on the right-hand side as the output of my function. And in fact, in theory, as you increase the number of hidden units in your network, so you make your network wider and wider and wider, we have more and more hidden units, a network with only a single hidden layer can actually represent any smooth function. So if you give me a function, I can give you a neural network that actually implements that function as its sort of computation. This is really cool. It gives you a hint as to why neural networks are so powerful, right? You can represent any function as a neural network, then your learning procedure then hopefully can learn to represent any function you might be interested in. Okay, so neural networks probably seem a little bit complicated, and they are. But I'll argue in this slide that a lot of times you might be able to kind of abstract away the details of how they're actually working. And what I mean by that is that we've already seen quite a few classification models, and you can think of all of these classification models in a very similar way. What these models do is they take in some feature vector X, they do some kind of black box computation on them, that's some computation, and then they output some number, either class probability for something like a logistic model or a neural network, or they output just a label for something like KNN. So you can really think of classifiers all in this sort of more abstract point of view. Neural network, just another example of a classifier. Okay, I think I'm going to just skip that text. I'll also point out here that this is a pretty cool example, illustrating the effect of increasing the number of hidden units in a neural network. So if we have 3 hidden units in a small neural network with a single hidden layer and 2 inputs, we see we get some pretty complicated decision boundaries already. These are clearly nonlinear boundaries. If we increase the number of hidden units to 6, we get an even more complicated decision boundary. And if we go all the way up to 20, we get something that is quite complex, and it's now almost certainly overfitting our data. It's getting perfect accuracy here. So this is just to illustrate that neural networks are very, very flexible classifiers, even with this relatively simple setup we have of just a single hidden layer. Okay, let's introduce a little bit of notation here, a little bit of math, just to sort of set the stage for working with networks a little bit further. So we're going to use the notation g of z to represent a general nonlinear activation function. So for all intents and purposes, we've been working with the sigmoid function, 1 over 1 plus e to the minus z, as our activation function, but there are other choices for z that we'll see later on as well. We're going to use h sub m of x to represent the output of the mth hidden unit in our network. So it's the value of the mth hidden node in our sort of graph. And to actually get the value for our mth hidden value, what we're going to do is we're going to apply that activation function g to a weighted linear combination of my features, where the weights wmj vary not only over j, so the sort of number of features that I have, they also vary based on m. So each of my m hidden units has a different weight vector associated with it. But this equation should look a little familiar, right? It's essentially just the logistic model that we saw previously, except we swapped out the sigmoid function for a more general activation function. So for example, if I want to compute the value of this hidden node, the mth hidden node, I have a collection of weights associated with that hidden node, which we represent as Wm sub 1, which is the weight connecting the first feature to the mth hidden node. I have a weight Wm sub 2, which is the weight associated with the mth hidden node, again, and the second feature vector, so on and so forth. And then we use Wm sub 0 to represent the weight connecting the bias node to the mth hidden node. So it's this weight here that doesn't get multiplied with the feature vector. And then, of course, we have the same thing for each one of these hidden nodes here. So there's another collection of weights for the first hidden node, so on and so forth. To get the final output of our network, what we're going to do is a really similar computation to what we just did, where we're going to take our activation function g and apply it to a weighted linear combination, except this weighted linear combination is now a combination of these new weights beta times the hidden outputs. So rather than doing a weighted linear combination of my original data, I'm doing a weighted linear combination of the values of my hidden nodes, where the weight associated with the mth hidden node I'll write as beta sub m. On the second line here, what I've done is I've just replaced h sub m with that expression I had on the previous slide. So we can see that even in a neural network with just two hidden layers, trying to write out an equation for this neural network is going to be complicated. So in practice, we often don't write out expressions like this for our networks. We'll see other ways of representing them. So in sum total, all of the parameters theta in our neural network can be written as follows. We have a vector of weights W1 associated with the first hidden node, a vector of weights W2 associated with the second hidden node, all the way up to a vector of weights W sub m associated with our final hidden node. And then we have an additional vector of weights beta corresponding to how we go from hidden units to the output of the network. It's often useful to represent all of the weights or all of the parameters in our network in terms of a matrix. So we'll write capital W for the weight matrix, say in the first layer of my network, where in this weight matrix, I have one row for each of my hidden units corresponding to the weights for that hidden unit. So this first row here is all the weights in the first, for the first hidden unit, so on and so forth. We of course got D plus one of these, one for each feature plus our bias term, and then one row for every hidden unit. We'll often write our data X just as a vector, as always, so this is just a feature vector. And it turns out you can write in a very succinct way, sort of this weighted linear combination of the data for each of my hidden nodes as a matrix vector multiplication of W times X. So if you guys are familiar with linear algebra, it's a very compact way of representing my computation. Then to get the value for each of the hidden nodes in my unit, I need to apply that activation function to each of those linear combinations represented here. And to do that, I'm just going to apply my activation function to each one of the components of that vector I computed in the previous slide. And then, of course, I can do something very similar for the weights in the output. So if I have a vector of weights beta associated with the output, and I write h of x for the values of all my hidden units. To get the output of my model, I just need to do beta times h of x. So this is just the dot product between these two vectors is what I'm writing here. This is just sort of a nice vector way of writing the same computation we've been doing. And then I apply that activation function once again to get the final output of my network. So I know we went a little fast through this matrix vector representation of stuff, mostly for the sake of time right now. In the next lecture, we'll review this, but it's good to at least have been introduced to it at this point. Okay, so what we've seen so far is that we can build really simple neural networks by just stacking together logistic models, where the hidden units are some function of the inputs that are learned from data, and the output values are then obtained by applying a logistic model on top of those hidden units. So again, it's this idea of sort of stacking a bunch of nonlinear models together. Our hidden units necessarily are using a nonlinear activation function in order to make sure our computation doesn't just result in a linear model at the end of the day. If our activation functions were linear, well, our neural network would just be a big linear function, and that's not a very good model. And we've seen a few examples showing that neural networks can generate pretty complicated output functions, which in turn allow us to produce pretty complicated decision boundaries. There's lots of questions here, of course, that we're going to be spending quite a few lectures addressing. So how do we actually train a neural network? You're probably guessing gradient descent, and you're right, but how do I get the gradient for my neural network? It's a very complicated expression. How do I possibly differentiate this thing? Um, we saw for even logistic models, getting the gradient is not a totally trivial task. So, how are we supposed to learn these things after all? We might also be wondering if we can have more than one output in our network. Maybe we want to do multi-class problems with a neural network. The answer, of course, is yes. Can we have more than one hidden layer? Can we use other nonlinearities besides the sigmoid? How should we design our neural network? How many hidden layers should we have? Things like this. This is often called sort of the architecture of the network. And might also want to use our neural networks with things like pixel data with images or things like text. And so throughout the rest of this course, we're going to see plenty of answers to these questions. And of course, anytime I say can here, the answer is, of course, yes. Okay, so to just wrap up in 30 seconds or so, we finished our discussion on logistic models and saw how they can be extended to multi-class problems. We could do feature expansions for logistic models, like polynomial feature expansions to get nonlinear decision boundaries. But choosing these features is, a quite difficult task. This led us to introducing neural networks, which are an extension of logistic models. And really, the intuition for these models that I'm trying to drive home here is that you can think of them as kind of learning new feature representations in an automatic, data-dependent way. So we'll go ahead and end here. I'll see you guys all in class on Monday. Have a good weekend.